When trying to understand the motion of an object, it can be helpful to visualize that motion graphically. And I want to take some time to go through a few scenarios where we plot an object's position versus time and velocity versus time. And hopefully in doing so can clarify some of the ways that we analyze these situations and how to interpret these graphs. So I've got a few scenarios. We'll just kind of go through one by one, and I'll kind of graph them and talk through the thought process behind it. The first scenario, we have a ball drop from a height of 10 meters. So let's start with the position time graph. Where is the ball located at every point in time? So in this case, the ball is dropped from a height of 10 meters. So we usually look at the beginning and end cases. This ball is going to start elevated. So its position is going to be at 10 meters, assuming this is 0 meters here. So it starts there, and let's assume it falls all the way to the ground. So at some later time, it's going to be located on the ground. Now I put 10 meters. We can assume it's in free fall. Turns out it takes an object about 1.4 seconds to fall from a height of 10 meters. If we use our delta or x final equation, we'd be able to determine that. And so let's call this, 1 second right about here. And so that'd be about 1.4 seconds. So this object is going to start and it's going to fall in free fall. So this is an accelerating object. Its velocity is going to change. And when we're looking at a position time graph, the slope of the position time at any point is equal to the velocity. So this object is going to start at rest with no slope, and it's going to finish having gained velocity in the downward direction. So it would have a negative slope at the end. So this end point, you should see some kind of downward slope. So when I'm plotting this, it makes sense that we would see a parabola shape as this ball approaches the ground. It's going to get steeper and steeper as it gets to 0, and that's representing the speed in the downward direction. So now the corresponding velocity time graph, we would know that since the slope is 0 at a time 0, it'll have a velocity of 0, and that velocity is going to continually move downward. A second after falling, it'll be at negative 9.8. So if that's negative 10 meters per second, then at a 1 second mark, it should be located at about negative 9.8 or negative 10. So my slope here, if I were to graph that, it would be something like this. All right, the slope of that graph would be the acceleration which is equal to negative 9.8 meters per second squared. And that'll be the slope of every single velocity time graph for a free-falling object like we see here. Let's move on to another one. Now we have a ball thrown upwards at 5 meters per second from a height of 10 meters. So if we look at the position time graph, we again start at the 10 meter mark, except this time it's not at rest. It's going to have some kind of positive slope. So we're going to have a positive slope here, which means if gravity's pulling it down, it's going to subtract velocity. So in 1 second, it's going to subtract 10 meters per second of velocity, which would make you realize that if this is the 1 second mark, at about a half second, it'll subtract 5 meters per second. So at the 0.5 second mark, we'll probably be at some higher position. It's gaining altitude. And we'll have a point here where there's going to be no slope anymore. The ball comes to rest somewhere around there. And in that next half second, gravity's going to add another 5 meters per second. So we should have another point at about twice the time where we've now got a negative velocity. And if we recall, when an object goes from the same elevation, it should have the same speed but opposite directions. And then this ball is going to continue to speed up, and it's going to get to the ground pretty quickly because it's already has a negative velocity. So I should have even steeper slope at the ground. So if I connect all this, we see we've got a parabola that's opening down. And the function would look like this. X final equals half of negative 9.8 is negative 4.9 t squared plus the initial velocity plus its initial position. If you graph that parabola, you would see that. Now the velocity time graph, this thing's going to have a positive 5 velocity. So let's put 5 meters per second here. That's where it starts. In 1 second of time, at 1 second, gravity will subtract 9.8 meters per second, or about 10 meters per second. So we're actually going to be down here at negative 5 meters per second a second later. So somewhere around here, which means if I connect my slope, we should have something like this. And at the half-second mark, at 0.5 seconds, that object is going to have 0 velocity, which if you look at your position time graph, it's got a horizontal slope. And it's also going to indicate that it changes direction. So we have a change in direction, and we also have 0 meters per second. We have no velocity at this highest point that the ball reaches. Let's go to another one here. Now we have a ball thrown downwards at 5 meters per second. So we have this object here. Again, we'll put it up here at 10 meters in height. It's already going to have a negative slope because the velocity initial is downward at 5 meters per second. So the slope has got to be a negative slope. And it's going to get to the ground pretty quick because it's going to keep speeding up. So we just get a piece of that parabola going down to the ground. And the velocity time graph is going to start at negative 5 meters per second, and it's going to continue downward at negative 9.8 meters per second squared of acceleration. Let's keep moving quickly through these now. Hopefully you kind of get a sense of what's happening. It's going to keep getting faster in the negative direction. Now let's look at a totally new problem here. And we've seen this problem on WebAssigns. You have a rocket accelerating off the launch pad for 3 seconds, then cutting the engine. So let's look at the position time graph. This rocket starts on the ground. So right away we know we have a point right here. Now it's accelerating, so it's going to increase its velocity, which means we're not linear. We have a curve, and it's going to gain velocity and move off the launch pad to a higher position. So let's put some time stamps here. 1, 2, 3, 4, 5, 6, 7, 8. Let's go 10 seconds of time just to get a sense of what's happening here. So after 1 second, this rocket is now already going 10 meters per second. After the second, it's going 20 meters per second. After the third, it's now going 30 meters per second. So 3 seconds in, it's gained all this velocity, and in doing so, it's also gained a lot of elevation. So we should be higher up 3 seconds later, and we should get there by gradually increasing our velocity. So that's the first part. That's the first 3 seconds. Then it cuts the engine. And at this point, we're now in free fall. We have an object that has a slope right here of positive 30 meters per second is the slope. And gravity is going to take away 9.8 every second. So if you look at it, a second later we're going 20. Then we're going 10. And then we'll be at 0 right around this point here. So this thing's going to taper off and lose all of its velocity 3 seconds later. All right, due to gravity being negative 10 meters per second squared, negative 9.8. So it's going to do that. And so we should see a free fall parabola to that point. And 3 seconds later, it will gain all that velocity back in the negative direction. So we should see the same downward slope here of negative 30 meters per second. And this thing's going to keep falling to the ground and you have an even higher velocity when it finally gets to the ground. So you kind of get a sense of what's happening to this rocket. Now let's look at the velocity. It starts at rest. As we talked about, it's going to gain every second about 10 meters per second. So after 1 second, it's now going 10, then 20, then 30. So we get a linear relationship of increasing velocity due to a positive 10 meter per second squared slope. So we're going positive 30, positive 20, positive 10. So we're gaining 10 meters per second of velocity every second. And then gravity is going to take over. And it's going to instantly start sucking away the same amount of velocity. So with a similar slope, we should be about back to where we were with gravity taking over. And at that 6-second mark, which was right about here, it should reach 0 velocity, and then gravity will continue to decelerate it. And it'll keep getting faster and faster in the negative direction. This is negative 9.8 meters per second squared. So you have, again, your change in direction is here. And at this point, we have a change in acceleration. From positive to negative. The rocket's pushing up, positive slope. Gravity's pulling down. The direction of the push or pull on that rocket will change when you see that point on that velocity time graph. All right, let's do one more problem here. This is a little bit of a funny one. It's kind of a combination of what we've seen. We've got a rubber bouncy ball thrown downward, starting at 10 meters. It's thrown downward, so it should have a negative slope at the start. And so gravity should pull it down pretty quick to the bottom. But it's a bouncy ball, so it's going to bounce. So it's immediately going to change direction. So we're going to see a ball popping up, and since it was thrown down, and let's assume it's pretty bouncy, we can say that gravity will actually, it'll go past its point, and it'll bounce again. And then maybe it doesn't bounce up as high the next time. And we've all seen this kind of pattern right here as it starts losing energy. And now let's look at the velocity time. Starts with a negative velocity. It goes even more negative due to gravity. And then it hits the ground, and this is where it gets a little bit funky. In a very short amount of time, it suddenly has all this positive velocity, probably even more than what it had before. So it's going to jump almost vertically all the way up to here. Again, our change in direction. At which point, gravity takes over again. And we get this slope all the way down. Now let's think about what happens here. It's going to continue falling. It's going to reach its peak and then keep going down, and then it's going to spike up again. So you get something like this happening every single time. Not quite to scale, but kind of an interesting look at it. Now, for what you guys would have to do, we're really only asking you to do something like maybe 4 at the start. Realistically, it's these first 3 that I want you to understand. But I figured a little more advanced graph might be beneficial in describing what's happening. These can be kind of tricky. Sometimes the graphs don't look like you think. The position times typically do look like what the ball's actually doing. But understand the velocity time, I think, is really when you start to get a good feel for how the motion is represented in the graphs. So hopefully this is helpful. Maybe a little further than we needed to go, but hopefully find some value in it. Good luck.